We'll start on the next slides, and hopefully that background noise isn't too bad. So we can go into presentation mode. So this is just part 2. I split the slides up, otherwise they get too big to download. I think the last slides were already 20 megabytes, and so if you have too many things and too many slides, it gets quite large quite quickly and then crashes your phone or tablet when you try to open it there. So this is then taking kind of a shift away. So we've talked about the basic thresholding, how that works, and applied it to a few different types of images. And now we'll go to a bit more of a machine learning approach to image processing. And so how can we use machine learning ideas to help us do a better job with a task like segmentation? So what we'll look at for our first example here is sort of a self-driving car kind of problem. So, you want to have an image of a street, and you want to do something very simple, like identify where the lines are on the road. And so what we have here is we have an image, and then we have another image, and this is what we would like our segmentation to look like. So if it works perfectly, we want it to find all of these lines and call them the foreground and call everything else the background. And so we want to put all the pixels that we have and classify them into one of two categories. And so that's sort of the start of the machine learning problem, where we really say, rather than we sort of tweak a threshold value until it looks good and say, now we've done a good job, we have the much more clear starting point of this is our beginning and this is our goal. And we want to get to the goal as efficiently as possible, and we want to always be able to measure how far away from the goal we are, rather than having sort of this qualitative, you looking at the result and saying if it's good or bad. And so this quantitativeness that we try to bring to the assessment of the threshold is not something new. This comes in any time you try to make sort of a decision where you end up with sort of true positive results. And so these are results that you correctly identified. So they are supposed to be straight lines and you called them foreground. So your algorithm worked. True negative, which are things that are not supposed to be straight lines that you called background. False positives, and that's where it's outside the straight lines, but you classified it as foreground anyways, or your algorithm did. And false negatives are values that are in the straight lines that are classified as background. And so all of these terms, of course, apply to medical problems, apply to credit card transactions. Anytime you're making a decision, you really end up with this schema. But for images, it also works quite well, where we can now see we have an image. We sort of take an arbitrary threshold here, a value of 0.5, and then we have these road lines. And so once we've done that, we're now able to group everything into true positive, true negative, false positive, false negative. And so we can go down and we can show the images, which are quite useful to look at, of all the true negatives are things that it said were not road, that were not in fact road. The false positives were the things that it thought were sort of lines that were. False negative and true positive. And so what you see here is that we did fairly well. We have a huge number of true negatives, but we also have a fairly large number of false positives and a fairly small number of true positives. And so even though this true negative number is high, the number of kind of false positives and false negatives is high enough that it probably didn't do a very good job. And so what we use to quantify these things, because if you tell someone that your algorithm had 37,000 false positives, that's not very meaningful. What you want to quantify is really sort of the recall precision, how well did it do compared to the task that it was looking at. And so one of the terms you'll run into here is called recall or sensitivity. And that's true positives over true positives plus false negatives. And precision, which is then true positive over true positive plus false positive. And so what the recall or sensitivity shows is for all the things that were in reality positive, so true positive are positive that you identified correctly, false negatives are positives that you identified incorrectly. So you said it was negative when in fact it was positive. And the precision is then much more focused on sort of the things that you called positive, how many of them were in fact positive. And so they sort of have slightly different effects. So sensitivity, you can kind of imagine, if it's there, how likely are you to see it? Where precision shows much more, if you found something, what's the likelihood you should kind of take it seriously or that it was correctly found? Cool. And so we can calculate these numbers quite easily from the results we just did. And we get a recall of 58, which is quite not terrible, but a precision from 0.02. And so how would you interpret that? Yeah.
The most what we detected was not so positive.
Yeah. So the things that we actually found, very few of them actually belong to the road. And so that's something that you can, even talk to a medical doctor who has no idea what this image is and say your test has a precision of 0.02, and they'll be able to tell you why that's such a bad test. And so it sort of gives you a reasonable way for talking about how something works and quantifying and ultimately comparing so that you can improve it. So the ROC curve, which is one of the things I mentioned at the very beginning, was actually invented during, it's called the receiver operator curve. It was invented during World War II with soldiers detecting objects in battlefield using radar. And so if you can imagine, going back to World War II, so in the 40s, you had this brand new radar technology where you sort of had a screen with a bunch of spots on it. And lots of noise in your system, lots of manually built amplifiers, lots of birds or clouds or things coming around. And so they needed a way to quantify, if we see a spot on our screen, how likely is it that it's a Nazi warplane or enemy fighter? And if we don't see a spot, how confident can we be that no warfighter is coming? And that you can see this is a very important criteria to be able to look at and to optimize for, because you don't want to have something where you're constantly ringing a false alarm, telling people there's going to be a bombing soon, but you also don't want to not miss a potential bombing that could be happening. And so a lot of this was about how can you tweak these tools so they offer the best trade-off between not finding too much and not missing too much. And so that's where they came up with this idea of an ROC curve, where you really have a curve, because in most of these systems, just like with our threshold, there are parameters you can tune. And so when we showed, this threshold here, this is one of many possible thresholds. We can change this threshold and we'll get a different number of, didn't like that. A different recall and a different precision. And so by tweaking these values, we can get different outputs in the system. And so we end up with this idea of an ROC curve. And so here we change the threshold between 0.1 and 0.9 and calculate this precision and recall for all of these values. We have this tiny table that shows up here where we see the precision and the recall for different thresholds. So if your threshold's really tiny, like 0.1, your recall is very, very high because you're sort of including, what does it say up here? Everything in the image, which means you're going to find almost all of the true cases because you're basically saying everything's true. Versus if you make this threshold really, really high, you'll then begin to say everything is false, and so your precision will start to go up. But obviously, either of those extremes is not a particularly great place to be. And so we see the curve where we end up with sort of a small bump here, and then it goes down again. And that's the distribution of sort of the precision recall that we have. The ideal is to be sort of in this upper right-hand corner. And so clearly we're very, very far away from that. If you're doing this in practice, you don't have to write all these silly loops. So if you use, what's going on? Sorry, not sure why that jumped around. You don't have to write all those loops like we had before up here, where you have sort of 4 threshold equals 4 real, 4 to come up with all the different categories. All of these problems have been packaged and solved for you before. And so what most of these tools have sort of decided to use is not this original form of the ROC curve, but rather another form where instead of precision and recall, you have true positive rate, which is the same as recall, and then false positive rate. And so the only real difference is that your goal is to be in the upper left-hand corner. So you want a false positive rate of 0 and a true positive rate of 1, rather than the upper right-hand corner. So if you're using Python, you have this package called scikit-learn, which does ROC curves for you. It's one of the functions inside. And you can then very easily make one of these plots. KNIME has the same functionality inside it. And you can now see that for the curve, it's sort of trying to get closer in this direction to the ideal value there. And the other nice aspect that we have is that with this representation for a unbalanced distribution, you have random guessing as this green line, which has been a very helpful perspective to have, because a lot of times you'll build really complicated models and you'll find out that the ROC curves are not significantly better than random guessing. And it's a depressing thing to find out, but it is very helpful in terms of knowing that your model isn't actually predicting or doing anything useful. It's just sort of spitting out random guesses that happen to sometimes be right, because random guessing isn't always wrong either. And so here you get this nice curve where you can then see, which point on this curve makes the most sense to operate. And so if you're trying to minimize the number of false positives, you would then try to kind of pick maybe a point here, so where you get the no false positives and a fairly high true positive rate. And if you're trying to minimize or maximize true positives, you might pick a point over there. But that basically the curve encompasses that intrinsic trade-off that you have between these two problems. What's now really cool is that we can take these techniques that we've covered last week, so these different filters, so we have Gaussian, median. Did you cover difference of Gaussians? That doesn't, okay. Difference of Gaussians is just about as simple as it sounds. So a Gaussian minus another Gaussian. So basically it just is a bit of an edge enhancement filter, but it's much smoother than a lot of the ones you typically deal with. But anyways, these are the different kind of filters you have. And you can now take your image where you have the goal you're trying to reach. You have no filter, you have Gaussian filter, you have difference of Gaussian filters, and you have median filter. And you apply all of them. And all of the images look different. Maybe you say in this one, the stripes look a little bit clearer, this looks a little more blurred out. But with the ROC curves, we now actually have an ability to measure which ones work best. And so we can go down here and we can make an ROC curve for each one of those images. And we now see how they compare with one another. And so you have sort of the no filter, the Gaussian, the difference of Gaussian, and the median filter. And each one of those is a different line. And so what do we learn from this image? Yeah? So difference of Gaussian is better, I think, everywhere except here. So if for whatever reason you wanted to be at 0 or very low false positives, it might not be the right filter. But for everything else, it's much, much better than all the other tools. And so for the other filters, you have trade-offs that need to be made so that, this curve is higher here, but lower there. And so if you think you might operate in this regime, maybe it's better. But if you're operating in that other regime, it's not as good. And so how can we go about quantifying which curve is actually the best when there's these trade-offs? Any idea? Yeah?
Would be something like the area under the ROC?
Exactly. So if you do the area under it, you get a nice measurement. Obviously, it doesn't account for where exactly you might be using it, but it accounts for kind of the overall behavior of the curve. And again, if you're using KNIME or scikit-learn, this is just a function you have, area, ROC, AUC score. So AUC means area under the curve, and you can then apply it, and we can see, as we observed, the difference of Gaussians is very high, so 0.87. The median filter and Gaussian filter are about tied, and no filter is higher than both Gaussian and median at 0.8. And so if you were to look at that, you would say there'd be no reason to perform a Gaussian or a median filter because it actually makes your results worse. Now maybe if you combine them with another step, it would then be much better. But at least at this point, there would be no reason to investigate that further. And so what this gives you is really the ability to compare these things and not have a subjective assessment of this one looks much nicer, this one looks much worse, but to actually be able to say, this has made my image better, this will make my segmentation task easier because it's gotten rid of a lot of the things I'm not interested in. So in terms of evaluating models, there's lots of different references to look at there. This is the two examples of this. There's obviously hundreds that you can go through where you can start to see where these things get applied, what you need to be aware of. And with this language of true positive, false positive, precision recall, ROC, and area under the curve, you can talk about a lot of different problems beyond sort of image segmentation and start to use a lot of different tools that are built for dealing with these kinds of tasks. So now, to get kind of back to the segmentation task, so we've covered the ROC things. We'll cover it a little bit next lecture as well. But now to get to kind of a multiple phases segmentation problem. So now we have a more difficult sample we're working with, where it's made up of not just foreground and background, it has 3 different types of phases. And so here it's an X-ray tomography of a shale sample, and there's clay, rock, and air. And so our sample looks like this, where part of it is where you see the different intensity values. The really bright values are rock, the gray is sort of shale, and the dark values are air. Ideally, we try to derive 3 values for thresholds based on models, so we know what rock is made of, we know what clay is made of, we know what air, and so we could try to come up with 3 different values based on the alpha coefficients from those materials, but that could be quite time-consuming to come up with in the first place. It might be very imprecise because these are heterogeneous materials that have different densities and thicknesses at different spots. And so there's probably not exactly one value we'd come to. It's probably a range of values. And the histogram, when we look at it, doesn't even look like it would be something that would make this task particularly easy. And so if we take the histogram from sort of 0 to 1, we, like we saw before, don't end up with a bi- or trimodal distribution. We just have one messy peak somewhere in the middle, and trying to figure out what separates the clay from the background and the foreground is not easy. Often with these histograms, you'll see weird spikes. And so one of the useful things to do is tweak the number of bins you have and see how the shape changes. And so if you end up with sort of the wrong divider, you'll end up with very uneven peaks like we had at the beginning, I think 129, where it's sort of jagged and sawtooth. Very few distributions actually look like that in real life. And so it's important to kind of adjust it and see if that distribution persists or if it's potentially the fact that the bucket size wasn't well matched to the data set. So we do this sort of simple rule-based segmentation like before, where we kind of come up with cutoffs based on our initial look at the data. We can now assign things into different categories, where we end up with shale, void, clay, and rock, each classified into a different group. And yeah, and so we now can examine these images in more detail. And some of the things that we see is that there are lots of artifacts that need to be dealt with. So we'll talk about that a little bit in the morphology part. And thresholds that we want to optimize further. And so with this image, what we would need to do is get a ground truth image for what's actually shale, what's actually clay, and what's actually rock, in order to quantify, using these ROC curves we had before, how well these threshold procedures actually worked, and then try to improve them or try to improve the pre-processing so that that can happen better. And so that's sort of the things you end up with when you're looking at multiple different phases that you're trying to segment, because it's not quite as easy as just a binary classification. You now need much more training data because you have to create the void, the clay, and the rock masks in order to do this well. So for the implementation, we won't really talk about this very much, but thresholds and segmentations are very easy because it's sort of a unary operation, and so it takes one input and creates one output. And all the approaches we've talked about so far are something that are called sort of point independently, or can be calculated in a point independent fashion, which means you can parallelize it or run them across a large data set very quickly. Filters and morphology always depend on neighborhoods, which means they are much more difficult to parallelize. And so these tasks can be much more time consuming when you're dealing with really large image data, while having a threshold is a very quick and easy task to separate. So for a number of different languages, that's sort of what this looks like. You know, if you're dealing with two thresholds, you kind of have to use these AND or join signals. For Python, you know, we have, as we showed before, this sort of simple numpy command where you just have greater than thresh. For standard Python, so if you're dealing with lists for whatever reasons, you have to use a slightly different representation. And then for Java and C++, where you start to get more performant code, you end up dealing with a lot more overhead for solving the same kind of problem. And then with KNIME, of course, the threshold implementation is just a single block. So there's no code to write at all. But that you can see that there's sort of a wide range of possible implementations, and that when you're doing things in languages like Java or C++, you have to constantly be aware of sort of this offset value and how you're addressing a value in a three-dimensional or two-dimensional or four-dimensional array in a linear fashion. And so it's one of the things that I strongly recommend people avoid doing unless it's absolutely necessary, because it's very easy to make mistakes when you're implementing things this way by switching an X and a Y or having this offset calculated in the incorrect manner. And you might not immediately see that it's done incorrectly and end up with a result that is mostly working but gives you wrong results in a number of cases, or flips or transposes the image in ways you don't expect it to. So sort of pitfalls with segmentation. So one of the things that commonly gets covered, particularly with CT imaging, is this idea of a partial volume effect. And so we'll show sort of two variations of this. The first is where we have the exact same sphere. And so basically we take a coordinate system and we define it from -1 to 1, and we define a circle radius 0.75. And so if you look at the Python code, it's a little tricky to read, but that you basically have sort of x squared plus y squared is less than 0.75. And so we end up with, based on the number of pixels we sample this grid with, a number of different images that have a number of different volume fractions. And so here with 10 pixels, we end up with a volume fraction of 32%, 20 pixels, 40%, 500 pixels, 44%. And so the actual object hasn't changed in size or volume fraction at all, but the perception of what that volume fraction is has changed because our ways of sampling it have become sort of less coarse. And that's one of the things you'll need to be aware of when you're comparing results from sort of different scanners or different resolution machines, that you can't simply quantify volume fraction and say that this is a scale independent number, because as you get into higher resolution detectors, even the exact same object will end up with a different volume fraction. And so this commonly happens if you have, a group of young mouse bones and a group of old mouse bones, and you have a high resolution scanner and a low resolution scanner, that you might scan the old bones in a high resolution scanner and the young bones in a low resolution scanner and try to compare those results. And then you'll end up seeing that there's a volume fraction difference, and you'll attribute it to the fact that it's different bones, when in fact it's probably, or could just as likely be, from the fact you use different scanners with different resolutions. You have the sort of same effect when you rescale images from 500 times 500 down to 15, that you have a number of apparent volume fraction changes. So that when you take this original image, you have a volume fraction of 44, and then as you scale it down and interpolate it, you end up not only with sort of a different apparent volume fraction as you downscale it, but you end up with these pixels at the border, which are partially filled. And so if you were to look at this sample, you would say there is quite a bit of material at 0, there's quite a bit of material at 255, and then there's a few objects at 120 which are potentially made of different material, somewhere between the 0 and the 255. And so if the 0 was air and the 255 was bone, you might say, look, we found all this tissue that's tissue because that's between bone and air, when in fact you had no tissue at all. You just had a undersampling of your data, so it appeared that there were some pixels between these two values. And that the more that sampling changes, and so this would be a real life example or a simulated example, but the real life example would be when you're looking at structures that are smaller than your system is able to resolve, that you won't be able to see the structures themselves, but you'll be able to see sort of the artifacts that they leave, which could be distracting for what you're looking at. So that if you're looking at really small holes in bone, but the holes are too small for you to see, it might look like that bone isn't as dense because you're just averaging over a bunch of small holy structures, where in fact the bone is very dense where the bone is, but where the holes are, it's not dense at all. And so you're kind of averaging over those things. And so these are just important ideas to be aware of when you perform things like segmentation and thresholding and then measuring volumes from them, because that is being affected by how your images are sampled. And so a lot of cases will cause these things to look differently. And of course, once we start getting into shape analysis, this will be even more important. because these are, again, exactly the same object, but that one is perfectly circular, and this one is starting to look very square-like. And that doesn't mean this one is any more square than that one, but if we were quantifying some circleness factor, we would see differences there that don't actually exist. So now to talk about morphology quickly, we'll utilize this information from neighbor voxels to sort of improve the results. And so the idea is that once we've done a segmentation, a lot of times the segmentation isn't complete or doesn't show us everything we want to see in the image. And so we can use morphology to enhance that segmentation to look better. And basically it's like filtering or like this image enhancement, but it only takes place on the already segmented image. And so what assumptions lie behind this is that sort of nearby voxels in real images are strongly related or correlated with one another. So sort of if you have, two voxels of heart tissue here, it's unlikely that one pixel next to it is all of a sudden a completely different type of tissue. It's very likely that that will also be heart tissue. And that, more importantly, noise and imaging artifacts are less spatially correlated. And so that noise is kind of a random process. And so if you include the fact that you expect nearby voxels to be similar, you can help reduce the noise that come up in images. And so here we'll take this example of this cross, where you sort of have a simple thresholding performed. So the simple thresholding performed just shows us that there's a cross here, but when you take a simple threshold, you end up with a lot of pixels outside the cross that shouldn't belong to it, and holes in the cross that should be filled. And so morphology are the tools that help us solve these problems. So the idea, the starting point for this is this neighborhood where, what is this region that you consider part of what you're looking at? And, a large neighborhood is more computationally intensive and can start to smooth out features. A small neighborhood is computationally cheaper, but then it struggles with large noise or filling large holes. And so the neighborhood is important for filtering, morphological operations, component labeling, distance map. It's often called structuring element. So for those of you using NumPy, SciPy, Scikit image, and MATLAB, I think they call it SELEM in it. That's sort of the more computer vision term for the same idea. But the idea is the neighborhood that you're looking at. And so neighborhoods in 2D sort of look like this. And so here's an example of, 4 or 5 different types of a number of different types of neighborhoods where, disk is sort of a relatively circular one in every direction. Horizontal line, vertical line, star, octagon, cross, all of which sort of encompass different assumptions about how the distribution in your sample looks. Many of them have uses in many different cases, but for the most part, disk is what we'll be using for this class unless there's specific reasons to use something else. So if we go back to this example from before, so we have this noisy image, and we're trying to get rid of that noise. And so here we have the noise as horizontally streaky salt. What sort of neighborhood would you use to get rid of horizontal streaks in an image? Any idea?
Probably a filter that is orthogonal.
Exactly. So if you use a vertical line filter, or I hope so, vertical line filter here, you can see here, it got rid of all of the streaks because it was just looking in the vertical direction. And so it was able to see that these streaks were huge artifacts in the pattern, and it didn't look at all in this direction. And so it was able to incorporate the fact that the information you want to keep was primarily in this direction. And so we see it got rid of all of those stripes very well, versus a normal filter which didn't do a very good job at getting rid of those vertical streaks because it was looking at sort of a whole box. And so when you can design the neighborhood to be better suited to your problem, you can do a much better job without damaging the image. I mean, if we go back to sort of the standard square median filter, to get rid of all the stripes, we don't get rid of it with 3, with 7. We'd get rid of it, but we've now smoothed over a lot of other parts of the image. And so we can potentially get rid of the noise with that filter as well, but we end up having to sacrifice a lot more on image quality because we weren't able to put our understanding of the fact that the noise is always coming in horizontal stripes. And so that's sort of the kind of issue where this becomes very important, is where you know something about how your detector works, how your reconstruction works, and what those artifacts are likely to be. So for erosion and dilation, if any erosion's fairly simple, if any voxels in a neighborhood are 0 or false, then the voxel will also be set to 0. And so this can kind of be imagined as peeling a layer off the surface of an object. Dilation is then very similar, but the opposite. And so what you do is add a layer back. And so if we apply it, we can take this original image, so this sort of diagonal line. If we apply a dilation, this line gets thicker at all the points because it basically goes around and says if any point around it is 1, then it's set to 1 as well. And we can then apply erosion to this image and see what happens to it. Does anyone have any idea what will happen when we apply erosion? So if we peel off a layer from this image, we just added a layer too. The original. That's a good guess? Yeah?
It depends how we treat those top corners, doesn't it?
Exactly.
Because if we count the outside of the image as not having anything, then we lose those 2. But if we do something different, then you keep them.
Exactly. So we end up with this problem that at these borders, it's kind of unclear what you're supposed to do. And this comes up in lots of different algorithms. Even for the exercises last week, if you looked at the median filter or the mean filter or the Gaussian filter, all of them have arguments for how you handle data outside the boundary. With neural networks, this is also a massive issue that has not really been unified or well solved yet in how do you treat pixels here. And so commonly what you do is you pad it with zeros, but if you pad this with zeros, you then end up deleting all of these pixels. And so we now end up with not quite the original image, even though we should have, or felt like we should have, applying an erosion and applying a dilation to a fixed structure shouldn't change it that much. That's, of course, where we get into opening and closing. And so opening and closing, our opening peels off a layer and then adds a layer back on. And what this does is it doesn't always keep your image exactly the same. It gets rid of sort of very small objects. Because if you delete something, if you delete a pixel that's standing by itself, in erosion, it can't come back when you dilate because there's nothing there. And so that's sort of why these operations work, is because if you delete small objects or if you add objects, even if you perform an erosion, afterwards they sort of stay around. And dilation closing is a dilation followed by an erosion. So you connect things together first, and then you peel a layer off. And so that objects that were very close will stay connected after you've done this. And the reason both of these are useful is because they have sort of volume preserving characteristics. Because if you perform dilation, you always have more pixels than you had before. If you perform erosion, then you always have less. But if you do these opening and closing, you have roughly the same number of pixels. You don't make your object universally thicker or smaller. Then for the next slides. The sort of examples from erosion and erosion and dilation on the cross image we have here. So these are from the slides from last week. They aren't in this slide deck yet, but they'll be moved in there soon. Where you can sort of see what that does for the cross, that the dilation sort of fills in all the holes, but also makes the cross bigger, and so it's not necessarily entirely desirable for everything there. Erosion does the same sort of thing, so it gets rid of all of these small individual pixels, but it also makes the cross itself smaller, and so that's not an effect that we want to have. And so this is where opening and closing come in, where opening sort of gets rid of all those small objects and keeps the core cross structure the exact same size. And closing fills in all of the holes without making the cross fundamentally thicker or bigger. And so that we see that those operations complement each other quite well and can be very useful for processing these kinds of images. So you can apply this to sort of a bone sample or a number of different images. Here, let's say we're trying to find the bone mass itself, that the first thing we need to do, if you want to find the ratio of bone to air, so the volume fraction, you need to figure out where is the whole bone area and how do we compare it. And so if you wanted to fill in all the holes, you could use dilation to do that. And so if you do a 3x3 closing, you end up with a lot of the smaller holes filled. If you then do a 7x7 closing, you start to fill some of the bigger ones. You can then do a 45x45 closing, and you end up filling all the holes, but you end up with this kind of weird artifact at the boundary. And so, again, that happened because of this problem that at the boundary you don't really know what happens. And so if you're doing closing, you dilate, and so you fill up all this area, and that doesn't necessarily get deleted again with the erosion. And so here we've started to fill that fairly well, but if we're trying to do contours, there's better approaches that will help us do contours efficiently. But we'll talk about those next time. So are there any questions on those topics so far? Okay. The one last thing I wanted to show in the exercises.